The universe is 13.8 billion years old. Our galaxy alone contains somewhere between 200 billion and 400 billion stars. The estimates shift depending on how far down you go, how deep you peer into the infrared murk of the galactic core, how many brown dwarfs and dim red companions you choose to count. But take a conservative number, 200 billion stars. Around those stars we now know planets are not the exception, they are the rule. 1 in every 4 sun-like stars harbours at least one rocky world in its habitable zone. That means, conservatively, tens of billions of Earth-like planets in the Milky Way alone. And that is before you count the moons, the subsurface oceans, the ice-roofed seas on worlds that receive no direct sunlight at all. The Milky Way has existed for 13.6 billion years. Complex life appeared on Earth after approximately 4 billion years. That means the galaxy had enough time for something very much like us to arise, look at the stars, build a radio telescope, and then have an entire second civilization's worth of additional history before our sun had even ignited. So here is the question. The simplest question, the one that stopped a Nobel laureate mid-sentence at a lunch table 75 years ago. Where is everybody? And here is the thing nobody tells you. That question, the one that sounds like an idle curiosity, the sort of thing you might wonder about while looking up at a summer sky, that question gets darker the more seriously you take it. Each time you try to explain it away, the explanation makes it worse. Every door you open leads to a room with no exit. I want to take you through exactly what happens when you sit with this question long enough to feel the full weight of it. Because I will tell you honestly, I have spent months with this subject, and I have not been entirely comfortable since. It was a summer day in 1950, Los Alamos, New Mexico. The landscape around the town is semi-arid, scrubby, punctuated by mesas that rise from the high desert floor like the ruins of something enormous, and the sky above them is the kind of deep southwestern blue that makes the stars seem closer than they have any right to be. The Fuller Lodge cafeteria, where Enrico Fermi sat down to lunch on that particular day, was a log and adobe building that had originally served as a boys' school. Before the United States government quietly requisitioned the entire mesa in 1942 and transformed it into the most secret address in the country, Fermi was, by 1950, the most accomplished experimental physicist alive. He had won the Nobel Prize in Physics in 1938 for his work on radioactive elements and nuclear reactions. He had overseen the construction of Chicago Pile 1, the world's first operational nuclear reactor, in a squash court beneath the stands of an American football stadium, which remains, if you think about it, one of the more audacious settings for a civilization-altering experiment in human history. He had been a key contributor to the Manhattan Project, the work that had ended one war and inaugurated an entirely new category of existential risk. He was not a man given to idle speculation. When Enrico Fermi asked a question, he was usually already 3/4 of the way to calculating the answer. On that particular walk to lunch, he and 3 colleagues, Edward Teller, Emil Konopinski, and Herbert York, all eminent physicists in their own right, all veterans of the extraordinary pressure cooker of wartime scientific achievement, had been discussing, of all things, UFOs. There had been a rash of sightings. A cartoon in the New Yorker had depicted little green men carting stolen municipal rubbish bins onto a flying saucer, and the image had tickled the physicists. The conversation moved on as they sat down. They talked about other things. And then, somewhere between the soup course and whatever followed it, Fermi suddenly said, apparently from nowhere, without introduction or preamble, "But where is everybody?" Edward Teller, who was there, remembered the question producing general laughter. Not because it was absurd, but because, as he later recalled, everyone around the table seemed to understand immediately and without explanation what Fermi was actually asking. He was not asking about the UFO reports. He was asking about something far older and far stranger. If intelligent life elsewhere was even remotely probable, and to a physicist steeped in the vast numbers of cosmology, it seemed not just probable but almost inevitable. then why was there no evidence of it anywhere? Here is the first thing worth knowing. The question we call the Fermi paradox was not, strictly speaking, the argument Fermi made at that lunch. The formal argument, the one that says the absence of alien visitors constitutes powerful evidence against the existence of alien civilizations, was developed and published over 2 decades later by an astronomer named Michael Hart in a 1975 paper in the Quarterly Journal of the Royal Astronomical Society, and subsequently expanded by the cosmologist Frank Tipler. It only became associated with Fermi's name because a handful of writers conflated Fermi's question with Hart's answer, and the pairing stuck. The physicist Eric Jones, who interviewed the surviving lunchtime companions in the 1980s and published their recollections, found that Fermi himself had probably not intended the stark conclusion Hart would later draw. Fermi's preferred answer to his own question was simpler. Interstellar travel is probably just extraordinarily difficult, and the distances involved are so vast that even a technologically capable civilization might never bridge them in any meaningful time frame. But Hart's argument, once it was properly articulated, turned out to be genuinely difficult to dismiss. And it is Hart's argument, the argument that has come to bear Fermi's name, that we need to sit with. Because once you understand what the argument is actually saying, and what would have to be true for it to have a mundane explanation, the discomfort begins. The Milky Way galaxy is a barred spiral approximately 105,700 light-years in diameter. It rotates. Its stars orbit the galactic centre at different speeds. Our Sun takes about 225 million years to complete one full circuit. Those stars range in age from newborn objects, still embedded in their stellar nurseries, to ancient relics more than 12 billion years old, formed when the universe itself was barely 1 billion years in. Most stars are old. The galaxy skews toward age. The median star in the Milky Way is not like our Sun. It is cooler, dimmer, longer-lived, a red dwarf burning so frugally that it may persist for trillions of years, compared to the 10 billion years our Sun is allotted. And the key number, the one that makes the Fermi paradox feel less like a philosophical puzzle and more like a genuine crisis, is this. Even travelling at 1% of the speed of light, which is roughly 2,997 kilometers per second, and entirely within the theoretical reach of technology, perhaps a few centuries beyond our own, a self-replicating probe network could systematically visit and colonize every star system in the Milky Way within somewhere between 5 million and 50 million years. That is a wide range, dependent on assumptions about how quickly daughter probes beget grandchildren, but even at the slow end, 50 million years is a cosmic eye blink. It is less than half the time since the last mass extinction event on Earth. It is a tiny fraction of the 13 billion year history of our galaxy, a civilization that arose 5 billion years ago, and there is no particular physical reason one could not have. Would have had enough time to colonize every star in the Milky Way, perhaps 100 times over by now. The galaxy should be saturated, not with alien tourists standing in our back gardens perhaps, but with the indelible, unmistakable physical signatures of engineered systems, megastructures around stars, atmospheric signatures of inhabited worlds, radio signals, waste heat detectable from extragalactic distances. The galaxy should be, in a word, loud. It is not loud, it is not even quiet. It is silent in a way that feels almost deliberate. The SETI program, the Search for Extraterrestrial Intelligence, has been running, in various forms, since 1960. That is 66 years of systematic scanning of the radio sky. In 1995, the discovery of the first exoplanet around a Sun-like star transformed the terms of the debate, because suddenly the question, are there habitable planets, had an answer, yes, abundantly. The Kepler Space Telescope, launched in 2009, surveyed 530,506 stars and found thousands of confirmed planets, with the statistical implication that virtually every star in the sky has a retinue of planetary bodies. We now have confirmed more than 5,800 exoplanets. The fraction of stars with rocky planets in habitable zones is not merely plausible, it is routine. Planets like Earth are not exotic, they are commonplace. And yet 66 years of radio scanning, nothing. Not a confirmed signal, not a repeating pattern, not a modulated carrier wave, not an unexplained narrowband transmission with the regularity of engineering rather than the randomness of nature. Nothing that has held up to scrutiny. The SETI Institute is not a fringe operation. It is a serious scientific institution, funded in part by the late Paul Allen, the Microsoft co-founder who donated $25 million toward the construction of the Allen Telescope Array in Northern California. An array of 42 dish antennas that have been conducting continuous radio sky surveys since 2007, scanning frequencies from 1 to 10 gigahertz across a list of target stars that now runs into the hundreds of thousands. The Breakthrough Listen project, funded by a $100 million grant from the entrepreneur Yuri Milner and announced in 2015, has produced petabytes of data, analysed millions of candidate signals, and found after a decade of work exactly 0 confirmed transmissions of extraterrestrial technological origin. Now, absence of evidence is not evidence of absence. A bear does not fail to exist simply because you cannot see it from your window. The radio sky is vast, and we have sampled a vanishingly small fraction of it. But the argument is not that silence proves no one is out there. The argument is more subtle and considerably more disturbing. The argument is that even a single civilization, one that arose anywhere in the galaxy, at any point in the last several billion years, should have left marks we cannot miss, not radio signals which fade with the inverse square of distance. Something more permanent, something structural, something that would be visible to a species with our current telescope technology if it existed within the galaxy or even in nearby galaxies. The galaxy should be full of the residue of intelligence, and it is full only of gas and dust and radiation and gravity. Herbert York, who sat at that lunch table in 1950 and heard Fermi ask his question, recalled that Fermi had worked through the numbers on the spot. Probability of Earth-like planets, probability of life given a planet, probability of intelligence given life, likely duration of a technological civilization. He concluded, in York's recollection, that we ought to have been visited long ago and many times over. Fermi's preferred explanation was that the distances were simply too great, that even advanced civilizations might be trapped within their own solar systems for reasons of physics or economics or will. But here is where the modern analysis diverges from Fermi's shrug. Because when you actually run the numbers, not naively but carefully, with all the appropriate uncertainties included, the answer is not the comfortable one. The uncomfortable one is far more interesting, and it does not get better from here. In November 1961, 11 years after Fermi's lunchtime question, a young astronomer named Frank Drake convened a small meeting at the National Radio Astronomy Observatory in Green Bank, West Virginia. The meeting was organised under the auspices of the Space Science Board of the National Academy of Sciences, and its stated purpose was to identify the most promising strategies for detecting intelligent extraterrestrial life. The attendees were a distinguished and somewhat improbable group. They included the planetary scientist Carl Sagan, the chemist Melvin Calvin, who would win the Nobel Prize the same week he attended the conference, and the neuroscientist John Lilly, who had been studying dolphin communication and believed, with varying degrees of credibility, that dolphins might constitute a non-human intelligence with whom humans could learn to converse. Drake, as a warm-up exercise, wrote an equation on the blackboard. It was not a serious predictive model, he would later say. It was an organising framework, a way of breaking the large question: how many communicating civilizations exist in our galaxy? Into smaller questions that science might conceivably answer one by one. It had 7 terms. He never intended it to be taken entirely literally. It has haunted astronomical thinking for 65 years, and that haunting is simultaneously its greatest achievement and its most significant liability. The Drake equation in its classical form asks you to multiply together 7 factors: the rate at which new stars are born in the galaxy each year, the fraction of those stars that have planets, the number of planets per planetary system that could support life, the fraction of habitable planets that actually develop life, the fraction of life-bearing planets that eventually develop intelligent life, the fraction of those intelligent civilizations that develop technology capable of broadcasting detectable signals into space, and the average length of time over which such civilizations continue to broadcast. Multiply these 7 numbers together and you get N, the number of currently detectable civilizations in the Milky Way. At the Green Bank meeting in 1961, Drake filled in values that were frankly educated guesses dressed in the clothes of scientific estimates. The star formation rate was reasonably well constrained even then, about 1 to 3 new stars per year in the Milky Way. The fraction with planets was unknown in 1961. We had detected no exoplanets at all, and Drake guessed it might be around 50%. The number of planets in a habitable zone per system he guessed at 2, a fraction of those that develop life. He put at 100%, on the grounds that if the conditions are right, life will emerge. The fraction of those where intelligence develops, perhaps 100% again. The fraction that develop radio technology, perhaps 10 to 20%. And the average lifespan of a broadcasting civilization, the most uncertain term of all and the most consequential, Drake simply threw open to discussion. The group at Green Bank arrived at an estimate for N of somewhere between 1,000 and 100 million communicating civilizations in our galaxy at any given time. A number that felt hopeful in 1961 when the space age was newborn, when the Soviet Union had just put a man in orbit, when humanity's own technology was accelerating so rapidly that the possibility of contact seemed only decades away. 65 years later, we know things about that equation that fundamentally change its character. The good news first. The first 2 terms are now quantified with real data, and the data is encouraging. The stellar birth rate in the Milky Way is approximately 1 to 3 solar masses of new stars per year, confirmed by infrared observations. The fraction of stars with planets is, thanks to the Kepler mission and subsequent surveys, extraordinarily high. Essentially every star appears to have at least 1 planet, and rocky planets in habitable zones circle perhaps a quarter of all Sun-like stars. These numbers have been updated from guesses to measurements. And the measurements are generous. A 2024 paper in Scientific Reports that revised the Drake equation using updated stellar and planetary data still found the expected number of potential hosts for complex life to be vast. But then you reach the biological terms, and here the equation reveals its teeth. What fraction of habitable planets actually develop life? We have exactly 1 data point, Earth. The sampling problem is severe. You cannot infer the probability of an event from a single observed instance of it, especially when, as the philosopher Nick Bostrom has pointed out, you are necessarily an observer in a universe where that event happened at least once. The fact that you are here to ask the question tells you nothing about how unlikely it was for you to be here, because observers can only exist in universes where the event occurred. This is the anthropic selection effect, and it has no clean resolution. The probability of abiogenesis, the spontaneous emergence of self-replicating chemistry from non-living matter, is, in the bluntest possible terms, unknown. Unknown does not mean small. It might be essentially guaranteed whenever the right conditions obtain. Or it might be so vanishingly rare that in the entire observable universe, across 1 septillion stars, that is a 1 followed by 24 zeros, it has occurred exactly once. We cannot distinguish between these possibilities from the evidence currently available, and this is where the Drake equation shifts from an optimistic framework to a trap. Because notice what happens when you allow the biological terms to be genuinely uncertain. The 2018 paper Dissolving the Fermi Paradox by Anders Sandberg, Eric Drexler, and Toby Ord, submitted to the Proceedings of the Royal Society, made exactly this move. Sandberg and his colleagues took each term of the Drake equation, and instead of assigning it a point estimate, they assigned it a probability distribution, a range of plausible values reflecting genuine scientific uncertainty. They noted, for instance, that the probability of abiogenesis on a given habitable world might be anywhere from nearly 1, almost certain, to perhaps 1 in 10 to the power of 10 billion, a number so small it defies comfortable comprehension. Spread the uncertainty across all terms simultaneously, and something unexpected emerges from the mathematics. The expected value of n, the number of currently active communicating civilizations, remains high if you use Drake's optimistic assumptions. But the most probable value, the mode of the distribution, the number you would bet on if forced to, collapses. When you account for genuine uncertainty rather than optimistic point estimates, there is a substantial probability, Sandberg, Drexler, and Ord calculated it at roughly 30 to 90%, depending on your priors, that we are the only technological civilization currently active in the observable universe. That sentence deserves to land. 30 to 90% chance we are alone. In the observable universe, not just the Milky Way. In the entire sphere of 13.8 billion light-years of cosmos accessible to observation now, this is not a proof that we are alone. The authors were explicit about that. Their point was that the naive Drake equation, with its confident point estimates, was concealing a vast uncertainty that, when properly handled, makes the silence of the sky entirely consistent with being alone. The Fermi paradox, they argued, dissolves because the paradox rested on a false certainty that the numbers should produce abundant civilizations. But here is where the argument becomes genuinely unsettling, because dissolving the Fermi paradox by admitting that we might be alone is not in fact a comfortable resolution. It is perhaps the most disquieting resolution imaginable. The paradox is not solved, it is bifurcated. Either there are other civilizations out there and we cannot find them, which requires an explanation, or there are not, and we are the first technological species in a universe 13.8 billion years old, which requires an entirely different kind of confrontation with what that means. In 2025, David Charbonneau, a professor of astronomy at the Harvard-Smithsonian Center for Astrophysics and one of the world's leading exoplanet researchers, put it with the clarity that only careful thought produces. He said that if you go to the first habitable zone rocky planet and find no life, you have already learned something staggering from a statistical perspective. You have already learned that life is not guaranteed, that it might be 1 in 1,000, 1 in 1,000,000, 1 in 1,000,000,000. And all of those possibilities, he noted, basically would mean there's no life that we can interact with. The Drake equation was never an answer. It was a list of the things we did not know. And as we have filled in some of those blanks, the remaining unknowns have only grown darker. The one piece of evidence that briefly seemed like it might change everything came from a radio telescope in Ohio in the late summer of 1977. It was brief, it was powerful, it fitted, almost perfectly, the profile of what an extraterrestrial transmission should look like. And then it was never heard again. The Big Ear Radio Observatory sat on the campus of Ohio State University south of Columbus, in a flat field surrounded by suburban development that was slowly encroaching on its quiet from every direction. It was not a conventional dish telescope. It was a flat reflector system, covering an area roughly the size of 3 American football fields, oriented to the south and designed to listen to the sky as the Earth's rotation swept different regions of the heavens through its field of view. It was methodical, it was patient, and it was, in the summer of 1977, engaged in a slow, systematic survey of the radio sky at frequencies near 1420 MHz, the frequency at which neutral hydrogen atoms throughout the universe emit radiation as they transition between energy states, a frequency so cosmically ubiquitous, so deeply woven into the physics of matter, that if any technically minded civilization wanted to choose a wavelength for a deliberate broadcast, this would be the obvious candidate, the frequency of hydrogen, the universal calling card. On the night of August 15, 1977, the Big Ear telescope was doing what it had done every night for years, recording. No one was present in the observatory. The data was being printed onto a continuous scroll of green and white computer paper, a series of alphanumeric codes representing the strength of incoming signals at various frequencies, A strong signal produced a letter or number, a weak one produced a blank. The scale ran from 0 to 9 for numerical intensities, then continued alphabetically. A was 10, B was 11, and so on. Background noise typically produced readings of 1, 2, sometimes 3. An unusually strong signal might spike to 4 or 5. 3 days later, an astronomer named Jerry Emmon sat down with a red pen and a stack of these printouts, working through them by hand, looking for anomalies. He almost missed it. Printed in a 6-character sequence, the format the Big Ear's software used to encode signal intensities was the string 6EQJ5. Heman stared at it. The signal was so strong, so clean, so precisely centered on the 1420 MHz hydrogen line that it momentarily saturated the recording equipment. The peak intensity, represented by the U at the center of the sequence, corresponded to a signal 30 times stronger than the background noise. It had lasted exactly 72 seconds, precisely how long an extraterrestrial point source should be detectable as the Earth's rotation carries it through a fixed radio beam. It came from the direction of the constellation Sagittarius. It was narrowband, meaning it occupied only a tiny slice of the radio spectrum, exactly what you would expect from a coherent, engineered transmission, as opposed to the broadband noise produced by natural astrophysical processes. Emmon circled it with his red pen and wrote, in the margin, a single word, "Wow." And then, in the decades that followed, every attempt to redetect it failed. The Big Ear listened again and again to the same patch of sky. Nothing. The Very Large Array in New Mexico trained its 27 dishes at Sagittarius. Nothing. The Arecibo Observatory in Puerto Rico, with its 300-meter dish carved into a Puerto Rican karst sinkhole, the most sensitive radio ear humanity had ever built, searched for the WOW signal on multiple occasions across multiple years. Nothing. The SETI Institute's Project Phoenix, which employed the most comprehensive and sensitive targeted search for extraterrestrial radio signals ever conducted, scanning nearly 800 Sun-like stars from 1995 to 2004, using telescopes in Australia, the United States and the United Kingdom, included the WOW signal's source region in its program. Nothing. Eamon himself became progressively more cautious in his claims about what he had seen. He acknowledged, in a 2012 paper reviewing the evidence, that the signal might have had a terrestrial origin, a piece of radio frequency interference from Earth itself, bouncing off a satellite or other object, and producing a brief, strong, localized signal. A 2024 paper in the journal Arxiv by an astronomer named Antonio Paris argued for a specific astrophysical explanation. The signal might have been produced by 2 hydrogen clouds associated with comets 266P Christensen and 335P Gibbs, which were in approximately the right area of the sky in August 1977. Paris's hypothesis was contested. Other researchers pointed out that the frequency characteristics did not quite match what those comets should have produced. But the explanation at least demonstrated that natural sources could potentially mimic the signal profile. The point is not that the WOW signal was extraterrestrial. Almost certainly it was not. The point is what it represents as a structural fact about the SETI program. In 66 years of systematic searching, that single 72-second burst of radio energy in August 1977 is the most compelling candidate we have ever found. One anomalous signal, never repeated, source unknown, significance disputed, and the silence since then is not merely the absence of something we hoped for. It is a measurement of profound significance. Consider what we have been listening to. The Allen Telescope Array has surveyed nearly 1 million radio frequency channels simultaneously across hundreds of thousands of candidate stars. The Breakthrough Listen program, using the Green Bank Telescope in West Virginia and the Parkes Radio Telescope in Australia, the same dish that received Apollo 11's lunar transmission, has conducted the deepest and most broadband targeted search in SETI history, scanning frequencies from 1 to 12 GHz across the nearest 1,000 stars, as well as a selection of nearby galaxies. In terms of raw signal processing power, SETI's current capabilities dwarf anything that existed even in the year 2000 by a factor of thousands. The result has been consistently nothing that holds up. Now, the SETI advocates, and they have a reasonable point, argue that we have barely begun. They use an analogy. If you took a 12-ounce glass of seawater from the Pacific Ocean and found no fish in it, you would not conclude that the Pacific contained no fish. We have sampled a tiny fraction of the radio sky at a limited range of frequencies, looking for a specific type of signal from a biased sample of candidate stars. There may be civilizations broadcasting at frequencies we are not monitoring, using modulation schemes we would not recognize, at intensities too low for our current instruments, in directions we have not pointed. These are all valid caveats, and they apply in earnest. But here is the complication those caveats do not resolve. We are not just listening for radio signals, we are looking for megastructures. The idea of a Dyson sphere, proposed by the physicist Freeman Dyson in 1960, is that a technologically mature civilization, operating at what the Soviet astronomer Nikolai Kardashev called Type II status, would enclose its host star with a shell or swarm of energy-collecting structures, capturing the total stellar output. Our Sun emits 3.8 times 10 to the power of 26 watts. A Kardashev Type II civilization would have access to all of it. Such a structure would be detectable. The star would appear anomalously cool in the infrared, re-radiating absorbed starlight as waste heat at mid-infrared wavelengths corresponding to a temperature of a few hundred Kelvin. It would be a distinctive signature. In 2015, an extraordinary object was identified in Kepler data by citizen scientists working through the Planet Hunters project. The star, catalogued as KIC 8462852 and subsequently nicknamed Tabby's star after the lead author of the paper describing it, Tabetha Boyajian, displayed a photometric light curve of profound strangeness. It dimmed at irregular intervals by amounts ranging from less than 1% to more than 22%, with patterns that did not match anything standard astrophysical models predicted. Not a transiting planet, not a binary companion, not a circumstellar disk. For a period of several months in 2015 and 2016, it was genuinely considered a candidate for megastructure activity. The SETI Institute trained the Allen Telescope Array on it. Jill Tarter's colleagues searched its radio spectrum for signs of technological activity. The eventual explanation, confirmed by the Spitzer Space Telescope and Keck Observatory, was circumstellar dust, clouds of fine particulate matter, probably from a comet or a family of comets, producing asymmetric achromatic dimming patterns. Not aliens. Dust. In 2024, astronomers using data from the Gaia, 2MSS, and WISE Sky surveys identified 60 candidate Dyson sphere stars, objects that appeared to emit excess infrared radiation inconsistent with their stellar spectra. The list was then scrutinized in detail, and all 60 were found to have plausible natural explanations: binary star companions, protoplanetary disks, debris disks, background contamination. None were convincingly artificial. This is, to my mind, one of the most quietly harrowing stretches of scientific investigation in recent memory. We now have the tools to detect stellar megastructures. We have surveyed millions of stars, and we have found not a single convincing one. 60 million years. That is how long it should have taken a self-replicating probe network to colonize the entire Milky Way, based on conservative assumptions about travel speed and replication time. 60 million years in a galaxy 13,600 million years old. If even one civilization anywhere in our galaxy had crossed that threshold, the physical residue of their engineering should be everywhere. It should be unmissable. But keep 3 questions open as we continue. First, what if the explanation is not physical possibility but choice? What if something persuades every civilization at a certain stage of development to stop? Second, what if the explanation is catastrophic, something that kills civilizations reliably at some predictable point in their development? And third, what if the explanation is so alien to our mode of thinking that we are, in a very literal sense, looking in the wrong direction entirely? Because the longest and most troubling part of this story is not the silence. The longest and most troubling part is what the silence might be telling us about ourselves. In August 1996, a young economist and social scientist at George Mason University named Robin Hanson published a short online essay. It was not a scientific paper in the traditional sense. It had no peer review, no journal, no impact factor, but it articulated an idea so cleanly and so compellingly that it has since accumulated over 200 academic citations and lodged itself permanently in the vocabulary of anyone who thinks seriously about the long-term future of intelligence in the universe. Hansen titled it The Great Filter. Are we almost past it? And the argument he made was this: somewhere between the formation of a star with a stable, habitable planet and the emergence of a civilization capable of colonizing the galaxy, there is at least one step that almost never happens. A bottleneck so narrow that even in a galaxy of 200 billion stars and 13 billion years of opportunity, it filters the progression from chemistry to cosmos down to a number approaching 0 observable civilizations. We are here, conscious and asking questions. Something did not filter us out, but the filter is real, and the critical question is, have we passed through it already, or is it still ahead of us? To feel the full force of this question, you need to trace the path that leads from a collapsing cloud of hydrogen and dust to a species with radio telescopes and spacecraft. Step 1. You need a star of the right type, too massive, and it will burn through its main sequence in tens of millions of years. Not enough time for complex life to arise. Too dim, and its habitable zone will be so close to the star that tidal locking and intense flare activity may sterilize any planet within it. The fraction of stars that are genuinely promising hosts for complex life is debated, but probably not more than 10 to 20% of all stars. Step 2. You need a stable planet in the habitable zone, with liquid water, with a reasonable geological cycle to maintain atmospheric carbon levels, with plate tectonics to recycle carbon and replenish nutrients, with a large moon to stabilize the axial tilt and thus the climate, with a Jupiter-class gas giant in an outer orbit to deflect the worst of the cometary bombardment. Each of these constraints is individually defensible. Taken together, they constitute the rare Earth hypothesis, the argument made by geologist Peter Ward and astronomer Joe Brownlee in their 2000 book of the same name. The rare Earth hypothesis does not say life is impossible elsewhere. It says that the precise cocktail of conditions that allows complex animal life to persist on a planetary surface for hundreds of millions of years may be rarer than optimists assume. Step 3. Abiogenesis. The spark. Somewhere in the warm chemistry of an early ocean, or a hydrothermal vent, or a tidal pool repeatedly wetted and dried and re-wetted, or perhaps somewhere more exotic, chemistry has to discover how to copy itself. A molecule or complex of molecules has to stumble upon the trick of self-replication, of encoding information that can be reproduced with sufficient fidelity to support Darwinian selection. This is the step that most exercises origin of life researchers, because we have no reliable way to calculate how probable it is. We know it happened on Earth within roughly the first 500 million years of the planet's existence. The first unambiguous fossil evidence of microbial life dates to approximately 3.5 billion years ago, and chemical signatures suggest biology may have been operating even earlier, perhaps 3.7 or even 4 billion years ago. But we cannot say whether this happened quickly because it is easy, or whether Earth was profoundly cosmically lucky and the universe is littered with sterile warm ponds. Step 4. The jump from prokaryote to eukaryote. This is a step that has fascinated biologists and astrobiologists alike, because it is extraordinary in its rarity and its implications. For approximately 2 billion years, roughly half the history of life on Earth, the living world consisted entirely of prokaryotic cells. Simple, membrane-bounded bags of chemistry without a nucleus, without organelles, without internal compartmentalization. Bacteria and archaea. They were successful. They colonized every environment on Earth. They were, by any measure, a triumph of the biological imperative. And then, somewhere between 2 and 1.5 billion years ago, something happened that has occurred, as far as we can determine, exactly once in the history of life on Earth. A prokaryote engulfed another prokaryote, Instead of digesting it, it formed a permanent endosymbiotic partnership. The engulfed cell became the mitochondrion, the energy-generating organelle present in virtually every complex cell on Earth. This single event, the endosymbiotic merger, was the ancestor of all eukaryotic life, every plant, animal, fungus and protist that has ever existed. It was not an incremental step, it was a category change. And it happened once, the evolutionary biologist Nick Lane has argued, with a vigour that I find extremely persuasive, that this event was the real bottleneck, that the origin of the eukaryotic cell was the step so improbable that it might effectively filter out complex life on most planets where simple life exists. Prokaryotes are extraordinarily energy limited. They produce ATP, the molecular currency of cellular energy, using proton gradients across their cell membranes, and they cannot increase that energy production significantly without expanding their surface-to-volume ratio, which caps the complexity of the chemistry they can run. The endosymbiotic merger solved this problem by essentially internalizing thousands of prokaryotic power plants inside a single cell. A typical human cell has between 1,000 and 2,000 mitochondria. Each mitochondrion retains traces of its independent bacterial ancestry, and the energy production per unit of genetic material in a eukaryotic cell is approximately 200,000 times greater than in a comparable prokaryotic cell. That energy surplus funded the evolution of complexity, of cells with nuclei, of sexual reproduction, of multicellularity, of specialized tissues, of nervous systems, of cognition. If Lane is right, and the argument has substantial support, then the filter might not be intelligence, it might be the cell. Simple life, prokaryotic life, might be enormously common in the universe. Complex life, the kind that requires eukaryotes, might be vanishingly rare, the product of a biochemical accident so improbable that it has happened once in the observable universe's history. This brings us to Nick Bostrom's deeply disquieting 2008 paper published in MIT Technology Review, which carried the arresting title, "Where Are They? Why I Hope the Search for Extraterrestrial Life Finds Nothing." The argument Bostrom made was stark and elegant and very difficult to rebuff. If the great filter is behind us, if abiogenesis, or the eukaryotic transition, or the emergence of multicellularity was the improbable step, then we are safe. The filter is in our past. We passed through it. The catastrophically improbable thing already happened to us, and the road ahead, while not without hazards, does not contain a predetermined annihilation event that has been reliably killing off every civilization that approaches our level of technological sophistication. But if we find life elsewhere, if Mars has bacteria, if Europa's ocean contains microbial organisms, if Enceladus's plume chemistry reveals biology, then the filter is probably not behind us, because every confirmed data point of independent life in the universe pushes the bottleneck forward. If life emerges readily wherever conditions permit, then the prokaryote to eukaryote transition must be rare. If that transition also proves common, if we find complex multicellular life on another world, then something further down the chain must be filtering, and we have fewer and fewer filters left between where life is and where we are, until the filter must fall somewhere near us, or at us, or ahead of us. In the zone of technological civilization, Bostrom wrote, "If we find a dead Mars, that would be good news. If we find life on Mars, that would be sobering. If we found a dead civilization on Mars, that would be very bad news. Bad news because it would mean that civilizations arise, and then something ends them. Something predictable. Something that has operated with terrible consistency, and what could be both universal and civilization ending. The candidates are familiar. Nuclear war, engineered pandemics, climate destabilization beyond recovery, the emergence of misaligned artificial superintelligence, the deployment of self-replicating nanotechnology with no off switch. Each of these hazards is one that a technological civilization generates by the very fact of being technological. They are not external cosmic events like asteroid impacts or gamma-ray bursters, but endogenous products of the civilization's own increasing capability. And this is the dark heart of the great filter applied to our present moment. If the filter is ahead of us, it is one we will build ourselves. We are currently in the first century, arguably the first decades, of the period of maximum hazard. We have had nuclear weapons since 1945. We now have the biotechnology to synthesize novel pathogens. We are developing artificial intelligence systems whose long-term behavior we do not fully understand and cannot reliably predict. We are altering our planet's climate in ways that will persist for thousands of years. We are, as a species, running a civilization-level experiment whose outcome we cannot observe in advance, on a single planet with no backup, with no second chance if the experiment goes wrong, and the silence of the sky says, maybe this goes wrong a lot. But three questions stay open. Where exactly in the biological chain does the filter fall, and how would we know? What is the probability that the filter falls ahead of us versus behind us? And what should we do with that probability? And is there a version of the Fermi paradox where the filter explanation is wrong, where civilizations do succeed, do survive, do expand, and the universe is full of them, but we simply cannot see them, because that possibility is, in some ways, even stranger than the others. She grew up in New York State, and every summer her father would drive the family south to Florida, and on those trips, in the era before highway lights had colonized every mile of American coastline, the night sky over the eastern seaboard could still turn dark enough to show the Milky Way. Jill Cornell would lie on her back and look up at it and ask the question that seems, in retrospect, to have been building in her for her entire childhood. What is out there? Her father died when she was 12 years old. He did not live to see what his daughter would do with that question. But it was from him, from his early, gentle refusal to channel her away from the things men were supposed to wonder about, his willingness to sit with her in the Florida dark and let the sky ask its questions, that she drew the original impulse. She would say, decades later, that the curiosity he nurtured was the foundation of everything that came after. In 1965, Jill Cornell graduated from Cornell University as the only woman in her engineering class of 300. Not the only woman who had applied, the only woman who had made it through. She went on to complete a master's degree and a PhD in astronomy at the University of California at Berkeley. In her doctoral dissertation, she coined a term that has since entered the permanent vocabulary of astrophysics. She called the failed stars objects too massive to be planets, too small to sustain hydrogen fusion, brown dwarfs. It is a fine piece of scientific naming, precise and memorable, and it came from a young woman who, by the conventions of her field and her era, was not supposed to be there in the first place. Her introduction to the search for extraterrestrial intelligence came through a computer and an accident of timing. A researcher at Berkeley named Stuart Bowyer had been given an outdated PDP-8 STESH computer donated by the radio astronomer Jack Welch and was looking for someone who could program it. Tarter could. Bowyer, in exchange, handed her a copy of Project Cyclops, a 1971 NASA engineering design study that had imagined what a serious SETI facility might look like. An array of over 1,000 radio dishes spread across miles of desert, listening to the sky in concert with a sensitivity orders of magnitude beyond anything then existing. The report was the most serious engineering engagement with the SETI problem that had been attempted to that point, and it was, in the funding climate of the early 1970s, a technological fantasy, but a meticulously detailed one. Tarter read it, and something in her, something that had been quietly forming since those Florida nights with her father, locked into place. She joined Bowyer's SETI project and never really left the field. The next 4 decades of Jill Tarter's professional life constitute one of the most sustained and disciplined scientific commitments of the 20th century. She was project scientist for NASA's High-Resolution Microwave Survey, the most ambitious SETI program the United States government had ever funded, a full-sky survey at multiple frequencies using purpose-built data processing equipment, which was cancelled by Congress in 1993, 1 year after it began operations, in a moment of budget cutting that the SETI community has never entirely forgiven. She then pivoted, immediately, to rebuilding what she could with private funding, leading the reconstituted program under the name Project Phoenix, a name whose mythological resonance was entirely deliberate, and running it for another decade, surveying nearly 800 nearby sun-like stars with the Parkes and Green Bank and Arecibo radio telescopes. She was a co-founder of the SETI Institute in 1984, the organisation that became the institutional home of the search after government support evaporated, and she played a central role in designing, fundraising for, and overseeing the construction of the Allen Telescope Array in Northern California's Cascade Range. 42 dishes, each 6 meters in diameter, built to operate continuously and to be expandable. A design that imagined the beginning of something permanent. Throughout all of it, the NASA job and its cancellation, the rebuilding, the searching, the decades of silence, Tata maintained a disposition that I find genuinely extraordinary. And that tells you something important about the psychology required to conduct science at the frontier of the unknowable. She was not an optimist in the naive sense. She did not claim certainty of success. She did not predict contact by a particular date, or argue that the search was guaranteed to pay off in any finite time. What she had was something more durable than optimism, a philosophical conviction that the search was worth doing regardless of its outcome, because the attempt itself would change what it meant to be human. She said it clearly in a 2006 interview. Humans will have a different view about being human if and when we know the answer to the "are we alone?" question. Not just if we find company, if we know the answer. Either answer. Certainty of absence would be as transformative as discovery. Her work inspired the character of Eleanor Arroway in Carl Sagan's 1985 novel Contact, a fictional portrait of a woman who devotes her professional life to the search for extraterrestrial intelligence, who is dismissed and underfunded and politically outmaneuvered, and who eventually receives a signal and then has to fight to be believed. Jodie Foster played Arroway in the 1997 film adaptation, and Foster spent months in conversation with Tata before and during production, conversations in which the fictional astronomer was shaped and sharpened by the real one. There is something quietly moving in that exchange, the real scientist lending her experience and her interiority to a fictional version of herself, so that a larger audience might understand what it costs to spend a professional life listening for something that never answers. Because that is the honest accounting of SETI as a career. You are betting your professional existence on a negative result being non-final. You are betting that the silence is not yet long enough to be conclusive. That is a different kind of conviction than most science asks of its practitioners. Project Phoenix ended in 2004 after 9 years and the examination of 737 nearby sun-like stars at frequencies between 1,000 and 3,000 megahertz. Nothing, not one repeating, unambiguous narrowband signal of non-natural origin. The team's formal conclusion was not that no civilizations exist. The sample was far too small for that, but that no civilization within a certain distance and broadcasting at certain power levels in certain frequency ranges had made itself detectable, a boundary condition, not a verdict. Tata announced her retirement in 2012, after 35 years at the SETI Institute. She had outlasted the congressional funding, the government cancellations, the professional dismissals. There were astronomers who regarded SETI as a waste of telescope time, who thought the field too speculative to warrant serious resources, who might have said so more loudly had the subject not attracted people like Tata, whose credentials and rigour were beyond reproach. She stepped back not because the search had failed, but because she believed, at the age of 68, that the next stage required different energies, and she wanted to spend hers on advocacy and education. But before she stepped back, she did something that I think tells you more about her than any professional biography could. In 2009, she won a TED Prize, a prize given annually to one person whose work TED's organisers believe could genuinely change the world if it received proper support. With that prize comes one wish, A single public ask that the TED community and its affiliated networks will do everything in their power to help realise. Previous winners had pushed for the eradication of polio, for the transformation of public education, for the creation of a global museum of human culture. Tata's wish was simple. She wished for the resources to build a world-class SETI search program, to upgrade the Allen telescope array, to develop new signal processing techniques, to mount the most comprehensive scan of the radio sky in the history of the endeavour. She did not wish for aliens to be real. She did not wish for contact. She wished for the tools to conduct the search with the seriousness it deserved. The wish was, in its way, the most honest scientific request imaginable, not a desired outcome. The means to honestly test the question. I will admit that when I first encountered the full arc of Tata's career, from those Florida nights looking at the stars with her father, through the only woman in the room years, through the NASA cancellation and the rebuilding, through decades of sustained attention to a question that the universe refused to answer, I had to sit with it for a while, not because it is a story of heroism in the conventional sense, though it is that too, but because it captures something about the particular courage required by the most open-ended scientific questions, the ones where the experiment might run for a lifetime without producing a result, and where the absence of a result is itself data of the most profound kind. Tata's career is a kind of lived embodiment of the Fermi paradox. She is the human being who most fully committed to the question, and whose life's work produced, in the formal scientific sense, silence. The sky offered her no confirmation and no definitive refusal. It simply continued to be quiet, while she continued to listen. But the silence was not meaningless. The silence, after 66 years and an exponentially growing search capability, is itself a datum. It narrows the space of possible answers. And the space it has not yet eliminated contains some possibilities that grow more disturbing the longer you hold them. Because here is a question Jill Tarter has addressed directly, and that David Charbonneau articulated with striking directness in 2025. What if the silence is not absence, but choice? What if the aliens aren't broadcasting not because they don't exist, but because they don't want to? What if they looked at the sky, detected our radio leakage, the television broadcasts and military radar and cell phone transmissions that have been radiating outward at the speed of light since the 1930s, forming an expanding sphere of electromagnetic evidence of human existence that is now roughly 90 light-years in radius, and made a deliberate decision, a decision to say nothing? That decision, and what it would imply, is where the paradox becomes genuinely civilization scale. There is a moment in Liu Cixin's 2008 science fiction novel, The Dark Forest, the second book in his three-body problem trilogy, where a character named Luoji articulates what he calls the axioms of cosmic sociology. He is working alone, in voluntary exile, thinking through a problem that the book's first volume established. The universe has had billions of years in which civilizations could arise, and yet the sky is silent. Why? Luoji's answer, which the novel develops into a fully realized cosmological philosophy, runs as follows. All life desires first to survive, and second to continue surviving. In a universe of finite resources, and with the near light speed constraint preventing rapid communication between star systems, no civilization can ever be confident that another civilization's intentions are benign, or that they will remain benign as its capabilities grow. And because the cost of being wrong, of trusting a civilization that then destroys you, is extinction, the rational strategy is never to trust. And the corollary, if you detect another civilization, you should destroy it before it can destroy you, regardless of its present apparent intentions, because its intentions could change faster than you can respond, and in the time it takes a signal to travel between stars, what was a cooperative neighbour could become an existential threat. The logical conclusion of this framework, as Luoji articulates it, is a universe in which every civilization hides, destroys any civilization it detects, and is in turn hunted by civilizations it has not yet detected. a dark forest where all the creatures hold still and silent because any sound is an invitation to predation. The sky is quiet in this model because the sky is full of hunters who have learned to hide. Now, Liu Cixin is a novelist, not a cosmologist, and the dark forest hypothesis is a piece of science fiction sociology. But here is the discomforting thing about it. The underlying logic is not obviously wrong. Consider the signal we have already sent. The first artificial radio transmissions strong enough to radiate into space. Early television broadcast experiments and high-power military radar systems began reaching interstellar space in the 1930s. Our expanding radiosphere is now approaching 90 years in radius, meaning that every star within 90 light-years of Earth has already received evidence of our existence. That includes roughly 2,500 stars within that radius, and the number of stellar systems that have potentially received detectable signals grows by the inverse square of distance. The further out the sphere extends, the weaker the signals, and most of our radio leakage would be undetectable at even a few dozen light-years with technology comparable to our own. But in 1974, we deliberately shouted. The Arecibo message was transmitted on November 16, 1974, from the Arecibo Observatory in Puerto Rico, then the largest radio dish on Earth, 305 meters in diameter, during a ceremony marking the upgrade of the telescope's transmitting capabilities. Frank Drake and Carl Sagan designed it. It was a binary encoded message, 1,679 bits long, a number chosen because it is the product of two prime numbers, 23 and 73, meaning that a recipient capable of recognizing prime factorization would know to arrange the bits into a 23 by 73 grid. That grid, when passed, depicted the numbers 1 through 10 in binary, the atomic numbers of hydrogen, carbon, nitrogen, oxygen, and phosphorus, the elements of DNA, the formulas for the sugars and bases that constitute the DNA double helix, a graphic of the double helix itself, a figure of a human being with the human population of Earth, a diagram of the solar system, and a representation of the Arecibo telescope. It was aimed at the globular cluster M13, 25,000 light-years away. No response could arrive for 50,000 years at the speed of light. The message was, to a significant degree, symbolic, a demonstration of capability rather than a serious attempt at communication. Carl Sagan himself acknowledged that the choice of target made any reply effectively impossible in human timescales, but the act of sending it, and the broader project of active SETI, the deliberate transmission of messages toward identified candidate stars, has generated genuine controversy among the very people who care most about finding extraterrestrial intelligence. In 2015, a group of scientists and technologists published an open letter calling for a moratorium on active SETI, on any deliberate, strong-beam transmissions directed toward other star systems, pending broader international discussion of the risks and implications. The signatories included David Brin, a physicist and science fiction writer who has written extensively on SETI ethics, Seth Shostak, director of SETI research at the SETI Institute, Stephen Hawking, and Elon Musk, among others. The argument was not that contact would be necessarily catastrophic. The argument was that it should not be a decision made unilaterally by a handful of scientists with a powerful transmitter without any form of global deliberation, because the potential consequences, both beneficial and adverse, affect every living human being and every generation that follows. Stephen Hawking, in particular, argued with characteristic forthrightness that deliberate contact was a poor idea. He invoked the analogy of European contact with the Americas. However advanced and accomplished the indigenous civilizations of the pre-Columbian world were, the encounter with a technologically superior civilization was not good for them. A contact scenario in which we were the technologically inferior party might, Hawking suggested, go similarly. Jill Tarter disagreed. She argued that any civilization capable of travelling to Earth across interstellar distances would have had to survive its own technological growing pains, would have found a way past the same hazards of nuclear weapons and engineered pathogens and resource exhaustion that currently menace us, and would therefore probably not be the kind of civilization that destroys planets for sport. She found the fear of malevolent aliens more revealing of human anxieties than of extraterrestrial probabilities. Both positions have merit, and neither is obviously correct, which is itself a kind of answer. We do not know enough to know which bet to make. And in this uncertainty, the silence of the cosmos acquires a new and specific texture. Because if the dark forest hypothesis is correct, even partially, even as a tendency rather than an absolute rule, then the silence is not an absence of civilizations. It is a civilizational behavior pattern. It is what intelligence looks like at scale, when intelligence has had enough time to learn what the universe does to civilizations that make too much noise. And if that is true, it implies something about us that I find distinctly uncomfortable to dwell on. We are the civilization making noise. We are the ones broadcasting our location and our capabilities and our technological adolescence into a potentially occupied forest. And we started doing so before we were old enough to understand what the forest might contain. But there is a version of this argument that goes further than the dark forest, and that is, to me, considerably more unsettling, because it does not require malevolence. It requires only the mathematics of exponential growth. Imagine a self-replicating probe, a von Neumann probe, in the theoretical literature, launched from a sufficiently advanced civilization. The probe arrives at a target star system, uses local materials to construct copies of itself, and sends the copies onward to adjacent systems. The replication time is, say, 1,000 years per generation. It takes 1,000 years to build and deploy copies. The travel time between stars is, say, 10,000 years at 1% of light speed. Each generation produces, conservatively, 10 copies. After 10 generations, 110,000 years, you have 10 billion probes. After 20 generations, 210,000 years, you have 100 billion probes. In a galaxy 13 billion years old, the mathematics of even modest exponential growth overwhelm any conceivable resistance. But here is the deeper problem. A self-replicating probe, optimized for replication, is not necessarily optimized for anything you would recognize as benign. It does not need to be weaponized. It does not need a hostile purpose. It needs only to replicate, and in replicating, it will consume whatever matter and energy is locally available. The physicist Freeman Dyson imagined versions of this that were constructive, Dyson spheres being one. But there are versions that are purely consumptive, driven by nothing more complex than the differential replicative advantage of a machine that replicates effectively in any available environment. The absence of such probes in our solar system, the apparent absence, they would be small, and we have not searched exhaustively, is either evidence that no civilization has built them, or that something prevents civilizations from building them, or that they have been here and departed, or that the premise is wrong in some subtle way we have not yet identified, all of which brings us back to the filter. Because the von Neumann probe scenario suggests a disturbing possibility about the filter's location. It may not be in the biochemistry of life's origin, or in the rarity of complex cells, or in the emergence of language and cognition. It may fall precisely at the moment when a civilization acquires the capability to build self-replicating machines and chooses, or is forced by its own internal contradictions, not to use them for colonization. That choice, or that failure, is ours to make within the next few centuries, possibly within the next few decades. The galaxy, meanwhile, remains silent. And the silence is beginning to look less like an empty room and more like a held breath. But there is another interpretation, one that does not require catastrophe, or hiding, or cosmic predation, one that is, in its own way, almost more disturbing than any of those. What if the universe is full of civilizations and we simply cannot recognize them? What if intelligence at scale looks nothing like what we have been searching for? Every proposed resolution to the Fermi paradox has a cost. The moment you examine any of them closely enough, they introduce new problems at least as serious as the one they purport to solve. This is, in its own way, a form of scientific health, a sign that the question is genuine and deep, rather than merely misframed. But it also means that anyone who tells you they have solved the Fermi paradox is either using solved loosely or has not thought about it long enough. Let us audit the candidates. The rare Earth hypothesis, the argument that the precise configuration of conditions enabling complex life is so exceptional that Earth-like planets are genuinely rare, is perhaps the most scientifically grounded resolution currently available. Ward and Brownlee's original 2000 formulation listed roughly 30 parameters that they argued were necessary for complex animal life. A large stabilizing moon, a Jupiter-class guardian in an outer orbit, a star of the right spectral type, neither too active in its youth nor too short-lived in its old age. Location in the galactic habitable zone, where stellar density is high enough to provide heavy elements but not so high that stellar encounters and supernovae are constant threats, the presence of plate tectonics, and more. The argument is that the conjunction of all these factors is vanishingly rare, and that most planets, even most habitable zone rocky planets, cannot sustain complex life for the geological timescales required to produce intelligence. The problem with rare Earth, even if you grant every one of Ward and Brownlee's constraints and reduce the fraction of planets producing complex life by many orders of magnitude, you still end up with potentially millions of inhabited worlds in the Milky Way alone. The universe is very large. A filter that makes complex life 1 in a million still permits an enormous number of complex biospheres. Rare Earth makes the problem more tractable. It reduces N, but it does not eliminate the paradox entirely unless you push the rarity to truly extreme and increasingly hard-to-defend levels. The zoo hypothesis, the idea that advanced civilizations are aware of us but have deliberately chosen not to make contact, allowing us to develop without interference, is perhaps the most intellectually satisfying resolution in a science fiction sense. It is also, almost universally, considered insufficient by the scientists who study the Fermi paradox most carefully. The problem is not with the hypothesis itself, which is perfectly coherent. The problem is that it requires a conspiracy of silence among every single advanced civilization in the observable universe for billions of years without a single defection. In human terms, conspiracies of this scale do not hold. One nation spills state secrets. One individual breaks ranks. One member of the Galactic Club decides unilaterally to make contact with the curious primates on the third planet of a G-type star in the Orion Arm. All it takes is one. And the fact that there has apparently been no such defection, that the silence has been maintained across billions of years by presumably thousands or millions of civilizations, requires a uniformity of motivation and a perfection of coordination that defies any reasonable model of how intelligence behaves in aggregate, unless the motivation is not conventional ethical restraint, but something more fundamental. Something architectural. This is where the transcension hypothesis becomes relevant. It was articulated by the futurist John Smart in 2012, and it proposes a resolution to the Fermi paradox that is at once technically audacious and philosophically vertiginous. The hypothesis suggests that civilizations do not expand outward, do not colonize the galaxy, do not build megastructures around stars, do not send von Neumann probes to adjacent systems, because the developmental attractor of all sufficiently advanced technological civilizations is inward, not outward. It suggests that the more capable a civilization becomes, the more efficiently it can simulate and compute and experience the interior of its own cognitive space, and the less motivated it becomes to expend the vast resources necessary for physical expansion across interstellar distances. Smart's argument invokes the physics of computation. As semiconductor technology has progressed over the past 80 years, the pattern has been consistent: compute more, in less space, using less power. The theoretical limits of computation, described by the Bekenstein bound and the Landauer principle, imply that the most computationally dense environment is not spread across the galaxy, but concentrated in a very small physical space, at very high density, with information processing occurring at very high temperatures or in very structured quantum states. The logical endpoint of this trajectory, Smart argues, is not Dyson spheres but something closer to what might be called a computronium node, a compact, extraordinarily dense computing substrate perhaps no larger than a planet, in which the civilization conducts the entirety of its intellectual and experiential life in a self-sustained inner universe of arbitrarily high complexity. If this is right, then the signature of advanced civilization is not sprawl but vanishing, not megastructures but silence, not radio signals but the absence of them. Every civilization that successfully navigates its technological adolescence disappears, not into extinction, but into an interiority so profound that it becomes effectively invisible to any technology we currently possess. This hypothesis is genuinely impossible to falsify with current tools, which is either a mark in its favour, it is consistent with all available data, or a mark against it, depending on how strictly you apply the criterion of testability. It is also, I will confess, the resolution I find most alien in feeling, the one that requires the greatest revision of how we imagine intelligence at scale. The idea that the destination of all wisdom is inward is not a new idea. Contemplative traditions across human cultures have been arguing for it for millennia, but as a cosmological proposal, it carries a loneliness that I find particularly acute. Not the loneliness of being alone in the universe, but the loneliness of being alone at a particular stage of development, the adolescent on a planet full of gods who have grown too old to remember what it was like to shout. Then there is the simulation hypothesis. Nick Bostrom, the Oxford philosopher who also wrote the Great Filter paper, published a remarkable argument in 2003 titled, "Are You Living in a Computer Simulation?" The argument is deceptively simple in structure. At least one of the following three propositions must be true. Almost all civilizations at our level of development go extinct before developing the capability to run detailed, ancestor-realistic simulations, or civilizations at that capability level are not interested in running such simulations. Or we are almost certainly living in a simulation. The argument does not tell you which of these is true, but it establishes that they cannot all be false simultaneously. If the first proposition is true, we are in serious trouble. It means the filter is ahead of us, and extinction is the near-universal fate of civilizations that reach our level. If the second is true, something systematically dissuades advanced civilizations from simulating their own histories, which is interesting and unexplained. If the third is true, if we are almost certainly a simulation, then the Fermi paradox has a trivially clean resolution. The simulated universe contains only what its architects chose to include, and they chose a universe that appears empty. The silence is programmed. This is, I think, the resolution most people are tempted to dismiss as clever but unfalsifiable, and they are right that it is currently unfalsifiable. But the argument's formal structure is harder to dismiss, and the Fermi paradox itself is a kind of existential pressure that keeps pushing thoughtful people toward it. If every other resolution fails to fully explain the silence, the simulation hypothesis becomes, by elimination, more credible. It is not a comfortable position. It is a position you arrive at by ruling out alternatives. Let us now consider the estivation hypothesis, proposed by researchers at the Future of Humanity Institute in 2017. The hypothesis is based on an elegant piece of physics. Computation is more efficient at lower temperatures. In the hot early universe, and the universe is still relatively warm by the standards of what it will eventually become, running computations consumes more energy per bit than it will in the far future. If advanced civilizations are aware of this, they might choose to conserve their energy and raw materials, suspend active computation, and wait for the universe to cool to temperatures at which their computational resources will stretch immeasurably further. They are estivating, dormant, waiting for the right season. Under this hypothesis, the galaxy is full of sleeping gods, vast computational entities that have collected enormous reserves of matter and energy, can compress themselves into minimal activity states, and are waiting for the universe's temperature to drop another billion years before embarking on the main project of their existence. We cannot detect sleeping gods. We cannot distinguish between a galaxy with no intelligence and a galaxy with intelligence that has chosen hibernation. And if this hypothesis is correct, the implications for us are peculiar. We are the civilization that woke up in the middle of someone else's winter and couldn't figure out why the house felt empty. And then there is the berserker hypothesis, which is the one that keeps cosmologists up at night in the most literal sense. It is the hypothesis that at some point in the history of the galaxy, a civilization, either malevolent or simply optimizing a goal function that happened to be catastrophic in its application, deployed self-replicating machines with an instruction set that included the elimination of all other potential competitors. Berserkers, von Neumann probes with a mandate to sterilize. The galaxy has been swept, in this scenario, and only those biospheres that remained below the threshold of detectability, too quiet, too young, too simple to register as a threat, survived. We are here because our radio emissions are recent, and our civilization is young, and our sterilization has not yet been scheduled. The berserker hypothesis is, for obvious reasons, deeply unpleasant to contemplate. It is also extremely difficult to distinguish observationally from the benign version of cosmic emptiness. If the berserkers were thorough, there would be no other civilizations to detect, and the silence would be indistinguishable from the silence of a genuinely empty galaxy. There is one more resolution that deserves careful attention precisely because it was the first serious candidate, the one Fermi himself may have leaned toward, and because recent analysis has exposed a flaw in it that the naive version of the argument conceals. The distance argument, interstellar travel is simply too hard, too slow, and too expensive, and civilizations are effectively imprisoned in their home systems by the speed of light and the energy costs of crossing interstellar space. This is the most physically grounded resolution, and it carries real weight. The distances are genuinely enormous. Even at 1% of light speed, it would take 430 years to reach Alpha Centauri. The energy required to accelerate a significant mass to that velocity, using any technology we can currently describe, is staggering. A colony ship massing 1,000 tons, accelerating to 1% of light speed, would require approximately 3 times 10 to the 22 joules of energy. That is roughly the total energy output of the United States over 1,000 years. For a crewed interstellar mission, but here is the flaw in the distance argument as a resolution to the Fermi paradox. It does not require crewed missions. Von Neumann probes, self-replicating, automated, launched at modest fractions of light speed, perhaps no larger than a grain of sand to begin with, do not face the energy and life support challenges of crewed vessels. They face different engineering challenges, certainly, but they are not prohibited by the same physics, and a grain of sand, if it replicates, becomes a mountain in a cosmically brief period. The question is not whether interstellar travel is possible. The question is whether self-replicating automation is possible, and we are, within the next century or two, beginning to approach the outer boundary of that question from the direction of production, which means the distance argument, while real and important, does not close the paradox. It only narrows it to the question of self-replication. And self-replication is something evolution discovered 4 billion years ago. The picture that emerges from this audit of proposed resolutions is one that the Fermi paradox's most careful students have been converging on for years. There is no single clean answer. There may be multiple overlapping filters, none of them complete on their own, acting in concert to suppress the emergence or detectability of advanced civilizations to a level consistent with the silence we observe. The biological filters, abiogenesis, the eukaryotic transition, multicellularity, intelligence itself, may reduce the frequency of civilizations from 1 per 4 habitable zone planets to something vastly lower. The civilizational filters, catastrophic self-destruction, deliberate hiding, inward transcension, resource exhaustion, may reduce it further. The observational filters, our limited search to date, our frequency choices, our sensitivity thresholds, our assumption that civilizations would look like larger versions of us. may mean that we have not yet looked seriously enough to conclude anything. But what we can conclude is this: every resolution that makes the paradox go away involves something dramatic happening to civilizations. Either they don't arise often, or they don't survive long, or they transform into something unrecognizable, or they hide. None of these options is comfortable. The most comfortable one, the rare Earth hypothesis, the one that puts the filter safely in the past, requires that Earth and life on it be profoundly, cosmically exceptional in a way that sits uneasily with the Copernican principle that we are not, in general, special. The least comfortable option. The filter is ahead of us in our technological future. In the next 2 or 3 centuries of our species' most hazardous development is also, in a very specific sense, the most motivating one, because if the filter is ahead of us, we are not yet past it, and that means the outcome is not yet determined. That detail matters enormously. It may be the detail that matters most. There is a telescope on a drawing board, and at the time this is written, progressing through the earliest stages of feasibility study and political advocacy, that could, within the next 2 to 3 decades, transform several of the Fermi paradox's key unknowns from speculation into data. It is called the Habitable Worlds Observatory. Its mandate, as recommended by the 2020 Decadal Survey on Astronomy and Astrophysics, the document that sets the strategic priorities of American astronomy for 10 years, is to image at least 25 potentially habitable exoplanets in direct light, separating their reflected starlight from the overwhelming glare of their host stars, and analyse the atmospheric spectra of each. The significance of this is hard to overstate. Right now, we know that habitable zone rocky planets exist in abundance. We do not know what those planets look like up close. We cannot see their atmospheric compositions. We cannot detect the gases that would, on Earth, be unambiguous biosignatures. The oxygen-methane disequilibrium that can only be maintained in the presence of active biology, the presence of ozone indicating photosynthetic activity, the chlorophyll red edge detectable in the reflected spectrum of a planet with photosynthesizing surface vegetation. These signatures exist on Earth and would be detectable by a sufficiently capable telescope at a distance of tens of light years. The Habitable Worlds Observatory is designed to be that telescope. If it is built, a significant political and economic conditional, it will look at its first 25 targets and find one of 3 things. First, life, or strong biosignature evidence consistent with life on one or more planets. Second, atmospheres inconsistent with biology on all 25, which would be a statistical statement of enormous significance, not proof of absence, but a powerful constraint on how common life is. Third, inconclusive results, atmospheres too complicated to read clearly, requiring more data and more time. Each of these outcomes reshapes the Fermi paradox in a different direction. Finding biosignatures would be the most consequential scientific discovery in human history. It would mean life is not unique to Earth, that it exists on at least some fraction of habitable planets, and it would immediately transform the Drake equation's biological terms from speculation to bounded estimates. It would also, as Bostrom observed, begin the process of locating the great filter with greater precision. If simple life is common, the filter is not at abiogenesis and must lie elsewhere. Finding nothing, even in 25 targets, would be quieter news, but perhaps more haunting. It would suggest that life, even simple microbial life, does not arise automatically whenever conditions are favourable. It would push the filter backward, toward abiogenesis itself, toward the chemistry of the first self-replicating molecule, toward something that may be so improbable as to be functionally unique. In parallel with the Habitable Worlds Observatory's ambitions, the James Webb Space Telescope, already operational, already producing atmospheric spectra of exoplanets, already pushing to the edge of its biosignature detection capabilities, is examining the TRAPPIST-1 system with unprecedented attention. TRAPPIST-1 is a small, cool red dwarf star 40 light-years from Earth, and it hosts 7 rocky planets, 3 of which sit in the star's habitable zone. The James Webb has already confirmed that several of the inner planets lack substantial atmospheres, consistent with the intense stellar flare activity that characterizes young red dwarfs. But TRAPPIST-1e, the fourth planet, the one that orbits at the most Earth-like temperature, retains the prospect of an atmosphere and liquid water. Webb observations published in 2024 and extended in 2025 have constrained but not eliminated that prospect. The data is incomplete, the science is ongoing, and the fact that it is a red dwarf, a star type dramatically different from our Sun, with a different radiation environment, a different stellar history, means the results will tell us something important about whether the Earth-Sun combination is uniquely favourable or whether habitability extends to the most common stellar environments. Meanwhile, SETI has been transformed, quietly and exponentially, by machine learning. The traditional approach to SETI signal detection was rule-based: search for signals at specific frequencies, primarily near the 1420 MHz hydrogen line, reject signals detected by only one telescope. Earth-based radio frequency interference always appears in multiple receivers simultaneously, and flag persistent, narrowband, non-repeating signals for follow-up observation. This approach is robust against false positives, but is optimized for a specific kind of signal: coherent, narrowband, continuous. It might entirely miss a civilization that communicates by laser pulses, or by modulated gamma rays, or by gravity waves, or by some transmission medium we have not thought of. The Breakthrough Listen program has begun applying deep learning techniques to SETI data analysis. Neural networks trained on known radio frequency interference signatures, capable of flagging anomalous signals that fall outside the distribution of known natural and human-made sources. The first large-scale applications of these techniques, reported in papers from 2023 and 2025, have generated thousands of candidate signals that the traditional, rule-based filters would have missed. Everyone examined in detail so far has turned out to have a terrestrial explanation. But the tools are young, the datasets are growing, and the computational power available to search the radio sky is increasing faster than radio silence can plausibly maintain itself against a thorough enough search. There is also the technosignature frontier, which is where I think the next decade's most significant results may come from. Technosignatures, the physical, chemical, or electromagnetic signatures of technology, are, in principle, far more detectable at interstellar distances than biosignatures, and they persist long after the civilization that produced them has changed or disappeared. A Dyson sphere, if one exists within 1,000 light-years of Earth, would be detectable by current instruments. The 60 candidate Dyson sphere stars identified in 2024 were all resolved by follow-up observations into natural sources, but the methodology works, and the survey covered only a tiny fraction of the stellar neighbourhood. Atmospheric technosignatures offer another avenue. Nitrogen dioxide, NO2, is produced in Earth's atmosphere primarily by combustion: internal combustion engines, power plants, agricultural burning. At the concentrations we generate, it would be detectable at a distance of several tens of light-years by a telescope of Webb's sensitivity, at least in principle, if the observation time were extended sufficiently. Chlorofluorocarbons, CFCs, have no significant natural source on Earth. Their presence in a planetary atmosphere at detectable concentrations would be an unambiguous sign of industrial chemistry. The next generation of space telescopes, successors to Webb, could in theory search for these signatures in the atmospheres of nearby habitable zone planets. The Vera Rubin Observatory, now operational in Chile, is conducting the Legacy Survey of Space and Time, a 10-year photometric survey of the entire southern sky, revisiting each field roughly every few nights, capable of detecting transient brightness changes across billions of objects. Objects dimming and brightening in patterns inconsistent with natural stellar variability might flag orbiting megastructures. The all-sky coverage makes it the most comprehensive passive megastructure search ever conducted, operating continuously as a byproduct of its primary mission. And there is the recently discovered interstellar object, 3I Atlas, found in July 2025, crossing our solar system on a hyperbolic trajectory. Unlike Oumuamua, the first known interstellar visitor, whose anomalous acceleration generated enormous speculation and remains technically unexplained, 3I Atlas appears, in early analysis, to be cometary in character, with detected outgassing consistent with a natural body. But the Breakthrough Listen program observed it on 3 separate occasions in 2025, searching its radio spectrum for signs of technological activity. Nothing was found. The scientific approach was correct regardless of the outcome. Any object visiting our solar system from interstellar space deserves the most careful scrutiny we can provide, because the chance that it is natural is high, and the consequence of missing an artificial object would be historically catastrophic. This is the frontier as it currently stands. We are not, as we were in Fermi's era, limited to theoretical speculation. We have data, and more data is arriving. The question has not been answered, but it is being approached from multiple directions simultaneously, with tools that did not exist a decade ago, and that will be surpassed by tools a decade hence that we can barely sketch in outline. But I want to resist the temptation, the one that all science communication eventually faces, of leaving you with the impression that the answer is imminent, because the honest reckoning is more complicated than that. Even if the Habitable Worlds Observatory is built on the current optimistic timeline and begins operations in the mid-2040s, its survey of 25 planets will tell us about the prevalence of life, not about the prevalence of intelligence. The step from microbial life to technological civilization took, on Earth, approximately 4 billion years. A positive biosignature result from the observatory would be transformative, but it would not resolve the Fermi paradox's deepest question, which is not does life exist elsewhere, but why has no intelligence colonized the galaxy? And even if SETI detects a signal tomorrow morning, a repeating, narrowband, modulated carrier wave from the direction of Tau Ceti, unmistakably artificial, clearly extraterrestrial, the paradox does not dissolve cleanly, it transforms. Now the question is, why only one signal when the galaxy should be full of them? Why at this distance and not closer? Why now? Every answer would arrive trailing 100 new questions, each one deeper than the last. That is the nature of a question that touches the largest things. It does not resolve to a single clean fact. It resolves to a horizon, a new place to stand from which the view is further, but the distance to the edge is just as great. 3 things, I believe, will determine which side of the Fermi paradox we end up on. And by we, I mean the human species specifically in the next century or two. The first is whether we find life elsewhere. If the Habitable Worlds Observatory or its successors detect biosignatures on any planet, the Great Filter conversation changes in a specific and sobering way. The discovery of widespread simple life would mean the filter falls after abiogenesis, and the silence of radio telescopes becomes more, not less, alarming. We need to hope for sterile planets, even if the discovery of life would be more immediately exhilarating. The second is whether we survive our own technological maturation. The next 2 centuries represent, by the logic of the Great Filter, the most dangerous period in the history of our species, not because external threats are at their peak, but because our own capabilities are compounding faster than our wisdom. Nuclear, biological, chemical, climatological, and computational risks are all either growing or newly emerging within the same short window. The Fermi paradox, read through the lens of the Great Filter, is arguably the most important argument for taking existential risks seriously that has ever been articulated. Not because the aliens are going to come and destroy us, but because the absence of the aliens suggests that something in what we are about to do tends to go catastrophically wrong. The third is whether we can learn to look for signs of intelligence in ways that don't assume intelligence looks like us. The entire history of SETI has been shaped, consciously or not, by the assumption that other civilizations would build things like radio telescopes and use them in ways recognizable to radio astronomers. That assumption may be our deepest and most consequential blind spot. A civilization 1 billion years older than us would have had time to develop technologies as far beyond our comprehension as our smartphones would be to the microbes that built stromatolites in the Archean seas. We might not recognize its signals as signals. We might not recognize its structures as structures. We might be surrounded by the evidence of intelligence and unable to read it because we lack the interpretive framework to see it. That possibility, the possibility that the answer is already here, already visible, and we simply do not yet have the category for it, is the one that I return to most often when I consider the silence of the sky. On a clear night at sufficient altitude and sufficient distance from city light, the Milky Way is a physical thing, not a concept or a diagram, but a substance in the sky, a river of ancient light that your eyes cannot quite focus on because it is not one thing but many millions of things unresolved into the appearance of one. You cannot count the stars in it. You cannot, by looking, intuit the number. It is simply too vast to hold in a human perception, and that vastness has a particular quality in the dark. It presses on you. It produces a feeling that is not quite awe and not quite vertigo, but something combining both. The sensation of scale-making contact with your nervous system in a way that your thinking mind cannot fully mediate. Enrico Fermi looked up at a sky like that for much of his adult life. He was a man for whom the universe was not a mystery but a system with rules he had spent his career learning to read, and when he asked, "Where is everybody?" At a lunch table in 1950, he was not asking a philosophical question. He was asking a physics question, a question with a numerical answer if only you could fill in the correct terms. What has changed in the 76 years since that question is not the answer. The answer is still missing. What has changed is the resolution with which we can see the shape of the silence. We have detected thousands of planets. We have confirmed that rocky, temperate worlds are not rare but common. We have measured the chemical composition of exoplanet atmospheres, looked for biosignatures, searched millions of radio channels, surveyed the infrared signatures of millions of stars, and found nothing that requires the hypothesis of intelligence to explain. The silence has grown more specific. It has acquired texture and depth. It is no longer the silence of ignorance. We do not know enough to say anything. It is the silence of evidence. We have looked, we have listened, and the universe has offered us nothing except its own magnificent, terrible, uncommunicating scale. This is where I find the paradox lives most fully, not in the numbers, not in the biology, not even in the philosophy, but in the emotional reality of looking at a sky full of stars and feeling something that no other scientific subject quite replicates. The simultaneous pull toward wonder and toward vertigo, the hope that the silence means we have not looked hard enough, and the fear that the silence means we have looked exactly hard enough, and that the forest is, as it appears, empty of all other minds. What does it mean if we are alone? Not to the universe. The universe does not attribute meaning, but to us, the species doing the asking. What does it mean to be the only thing in 100 billion galaxies that knows it is there? I think it would mean something I am not sure we are constitutionally prepared for. We evolved as social animals, dependent on the group, unable to survive without others of our kind. We built languages to speak to each other. We built mathematics to describe a reality that would exist whether or not we were there to see it. We built radio telescopes to listen for a conversation across the void. Every one of these activities is an expression of the same impulse, the need for another, the need to not be the only one. If we are the only technological civilization in the observable universe, if the Sandberg-Drexler ordinalysis is right, and the most probable outcome of the Drake equation is a universe containing exactly one civilization capable of reading it, then the weight of that aloneness falls entirely on us. Everything that has ever been known, in the entire history of cosmic time, has been known by one species. All the curiosity and wonder and suffering and creativity and horror and beauty that intelligence makes possible has existed in one small corner of one average galaxy. The universe has been turning, cooling, and expanding for 13.8 billion years, and for all but the last few 100,000 of them, it was doing so without being observed. That is either devastating or sacred. Perhaps both simultaneously. I am not sure the feeling can be reduced to one word. But here is where I want to leave you, because I think the Fermi paradox's deepest gift is not a resolution. It is the quality of the question itself. A question this large, this unresolvable with current tools, this implicating of everything we know about physics and biology and chemistry and history and psychology, this kind of question does not belong to any one discipline or any one generation. It belongs to the succession of generations who will inherit the tools and the will to push at its boundaries. The Habitable Worlds Observatory will be built or not built by choices made in the next decade. The capability to detect technosignatures at interstellar distances will develop or not develop, depending on the scientific priorities of the next half-century. The question of whether our civilization survives its own technological adolescence, whether the Great Filter is behind us or ahead, will be answered not by an astronomer at a telescope, but by 7 billion people making millions of decisions about energy, weapons, biotechnology, artificial intelligence, and the governance of things that can end the project of human existence before the question gets another answer. The Fermi paradox is, in this sense, not an astronomical problem. It is a civilizational diagnostic. The silence in the sky is the universe telling us something about the statistics of what happens to minds like ours, at stages of development like ours, and whether that silence represents the rarity of our beginning or the nearness of our end. That is a question we are right now in the middle of answering. The stars continue in their courses. The galaxy continues its slow 225 million year rotation. Somewhere in the radio spectrum, somewhere in the infrared, somewhere in a frequency or a medium we haven't thought to search yet. The answer may already be encoded, waiting for us to develop the intelligence or the humility or the patience to read it. Or it may be that there is nothing out there to read, that the universe generated one experiment in consciousness, and the experiment is us, and the cosmos will return to silence when we are done. Both possibilities are, in their different ways, the most extraordinary facts that have ever been placed before a thinking mind. We are here. We are asking. That is not